Special Andgles. Okay, so you don't have to write this. All right, you don't have to write this, but I'm going to write this. The sine, cosine, and tangent of almost every angle are irrational. I.e. decimals that go on forever. Which is actually kind of interesting. It means for most angles that you pick, you actually can't build that exactly perfectly. Does that make sense? We said sine, cos, and tan are cool because they serve as like an instruction of how to build something, right? If I tell you the tangent of an angle is 3/5, well, we know tan means what? Tan is always...
opposite over adjacent.
That's right. And so if you wanted to build this, you could just make a right angle triangle. And if you said we want to make this angle have a tangent of 3/5, what do we call this side?
The opposite.
So we'd measure that out to be 3 meters, say. And this side we would call the adjacent. So we'd have to measure it out to be 5 meters. And now that angle would have a tangent of 3/5. You'd have made that angle. Does that make sense? But for most angles, it doesn't work nicely. Really quickly, let's say we wanted to, again, you don't have to write any of this. Don't write any of this. But let's say we wanted to make an angle of 43 degrees, like Kayla gave me. If we wanted to make 43 degrees, on your calculator really quickly, somebody do the tangent of 43 for me. 0.9325, and it keeps going, right? Well, that means that the opposite would be 0.9325, I guess, ... And what would the adjacent be? Yeah, does that make sense? You could think of this as being over 1. So there we go. And then if we went to build it, no problem. If we wanted this to be 43 degrees, all we would have to do is make the opposite side how long? 0.9325, and then make the adjacent side 1. By the way, did I draw that well at all? No, I did not draw it well, but there we go. How's that semi-feel? Does that kind of make sense? But again, it's never going to be perfect. It's never going to be perfect because this decimal actually goes on forever. Now, as a practical thing, does that matter? No, because as a practical thing, can we ever measure anything exactly perfectly anyway? Does anyone take manufacturing here? Nobody? You pack of nerds. Not one person in this thing has ever been like, hey, I'd like to learn how to use a lathe. Did you? Okay. And like when you did it last year, did you ever use like the lathe, but like with the mechanized system so you can dial it in to like, within 1,000th of an inch kind of thing? Sure. But even then, 1,000th of an inch, right? If you're using a micrometer, if you're using like verniers or whatever, or calipers. But even then, it's not perfect, right? Does that make sense? But even still, there are a couple angles that do, in fact, give us perfect numbers. Some of them are really obvious. What's one that we definitely know gives a nice round number? 90. Take the sine of 90 degrees for me. What do you get? 1. Take the cosine of 90 for me. Okay. Take the tan of 90. Error. Interesting. But that makes sense, right? Because with the tangent, the whole point of 90 degrees is that, right? Like, there it is. We get a 0 in there. Anyway, we'll come back to that. Okay, so now look at this. Today we're going to look at some specific angles that give us exact values when we take the sine, the cos, and the tan. Does that make sense? And there's 2 ways to teach this. Today I'm going to teach it one of the ways, and tomorrow I'm going to teach it one of the other ways. Does that make sense? Today I'm going to teach it one way. Tomorrow I'm going to teach it a different way. But I want to imagine this. Let's imagine we have an axis here, and I want to imagine that we marked out 1 in each direction. This, of course, would be -1, right? And this, of course, would be -1. And then I want you to imagine, and ready, bear with me, we're going to draw a circle. And I'm going to cheat, because I can. Oh, that didn't look like a circle at all. I'm going to try again. That isn't centered at all, is it? Okay, ready? We ready? Oh my God, I hate you so much. Not you. Not you. You guys are cool. I mean, I hate this. Okay, how's that? That's close to centered. Can we at least fake that as being centered? Does it need to come to the right? Needs to come to the right? That looks great. That's fine. How's that?
Off center. Oh.
Okay, guys, I'm doing my best. All right? Okay. I want you to imagine that we draw a circle on an axis that has a radius of 1. We then would call this what we call the unit circle. It's called the unit circle because it's just a single unit, all right? It'd probably be better if we called it like the single circle or something. I don't know, the one circle. Oh, good. OneNote just crashed. Did you say yay? It's not like math is going away, guys. I just had to reopen it. But thank you for hurting my feelings. So circle with a radius of 1, and we call this the unit circle. Okay, so what does this have to do with angles? Well, we could imagine any angle could be shown on here. By drawing a radius. And of course, what's the radius of this circle? 1. So, for example, I could draw this here. That would be 1 unit of dimension. And this angle here would be theta. Does that make sense? I should mention, by the way, I don't know that I ever sat down and very explicitly talked about how theta is used to represent unknown angles. So did I mention that? Is everyone comfortable with that? We tend to use x's to show unknown sides or y's, but for angles we tend to use theta, the Greek letter. And we always measure, theta is the angle between the radius we draw and the positive x-axis. We always measure theta against the positive x-axis. So theta is the angle between the radius drawn and the positive x-axis. And the line is always exactly 1 unit long. And that's just, this becomes a useful way to express angles. Does that make sense? Becomes a useful way to express angles. Don't draw this, right? Promise? But if, for example, we drew a unit circle like this, even a big acute angle, a big obtuse angle, like say this angle here, which would be roughly how much? 90, that would be 180, and it doesn't quite get to 270, so that could be maybe what, like 240? So we could call that, say, 240 degrees. See where we start measuring? We start measuring at the positive x-axis. Does that make sense? We always measure from the positive x, and then we always draw it counterclockwise, anti-clockwise. the angle, no, not the angle is measured anti-clockwise or counterclockwise from the x. If you did measure clockwise, what kind of angle would that be? I could measure that as 240 degrees, or I could measure it as, what would that be? If I did decide to measure the wrong way, quote unquote. In math, what do we usually do to say, instead of going the way we're supposed to, we went the other way? We would call that number negative. You can have a negative angle. So the other way I could describe this is that could be 240 degrees, or it could be negative, and it'd be negative how much? Yeah, how did she do that? Is she just like a super genius? How did she know that that was negative 120? She subtracted it from 360. Because this spot here would represent 0 degrees, of course, but it would also represent a full rotation, which would be 360, right? This up here would represent how many degrees? 90, good. And then by the time we've gone here, we've gone completely around, so this would represent 180. This is the one that you may struggle to remember, 270, and then we get to 360. Thank you, ancient Babylonians who counted in 60s. Do you know that's why we use 360 degrees, but it's also why we have 60 seconds in a minute and 60 minutes in an hour? Because the Babylonians counted in 60s. You know what we count in? Tens, way better. You know why we count in tens?
Because we're better like that.
Because we're better like that, A. And B, because we got fingies, baby. Lets you count. Look at that. I'd like to never say the phrase fingies, baby, again. But even still, I just made myself profoundly uncomfortable. But anyway, how's that feel? Does that make sense? All of which is to say, we measure angles off the positive x-axis, and we measure them counterclockwise. Which means if you're going clockwise, that's not a positive angle, that is a negative angle. Does that make sense? It's a little weird that we go counterclockwise, but if you think about it, it makes sense. All of the numbers on the x-axis here are positive, whereas over here they are negative, and all the numbers on the y-axis up here are positive, whereas down here they are negative, which means that if we went this way, we're immediately going into the negatives. So it makes sense that we go up like this to make the angle positive. Does that make sense? If you think about it that way, I think it actually makes a lot of sense why they call that positive, even though it's counterclockwise, and we're used to thinking of clockwise as kind of positive, right? Wouldn't it be weird if clocks spun that way? That'd be weird, right? If we did what? So the question, let's see if I'm reading this right. What if we went 240 degrees this way? Could you do that? We wouldn't be that far, of course. That'd be 90 this way, then 180 this way. So that'd be about 240, right? So if we went like that, is that what you were asking? If that's 240 degrees, because we're going counterclockwise, it would be negative 240 degrees. And what's another way of saying negative 240 degrees? Positive 120. And that's two ways of saying the same thing in terms of where you end up. But of course, you get there differently, right? If I turn positive 240 degrees, right, versus turning negative 120 degrees, I might end up at the same place, but the journey to get there was different. Does that make sense? Did that answer your question? So when we talk about an angle, the question is, are we talking about how you get there or just where we end up? And in math, for now, we're just talking about where you end up. Does that make sense? How you get there doesn't matter. So for the moment, in terms of math, positive 120 degrees and negative 240 degrees, the exact same thing. But of course, they're not the same trip to that spot. Does that make sense? But we're not thinking about this as motion. We're just thinking about this as like something that's been drawn on the page. Does that make sense? Hopefully. Okay. Why do this? Why bother? why put angles on an axis like this? What do you think? Because we need to measure them somehow. Good. And we've always just measured them by cutting a circle up into 360 pieces, right? Which is fine. And then if you print that on a little piece of clear plastic, we can call that a protractor, and you can put it up against an angle, and you can measure that way, right? Which is fine. This is just another way of thinking about the same thing, but here's why we do it. Ready? Look here. You don't have to write this. Don't worry. We'll write this later. But we said that the unit circle itself lives here like this, and it's got a radius of 1, which means if I put this angle here called theta, and I put it there, does this have coordinates? It's on an axis, right? So does it have coordinates? Well, it must, right? And of course, to get there, we had to go over like this along the x-axis, right? So that would be the x value of theta, right? You don't have to write this. And then, of course, we had to go up and down, right? And so if we had to go up and down, then we would get the y value of theta, and it makes a triangle. And do we know how to work with triangles?
No.
Yes, you do.
No, I don't.
Specifically, what could we talk about with this? The other beautiful thing is, anywhere on this circle, what did we say the radius was? 1. So the hypotenuse is always 1. Does that make sense? So what we end up with is a triangle that is 1, and then the opposite is, so for every angle on the unit circle, we can say that the opposite is just its what? Its y value. Does that make sense? And what about its adjacent? Its adjacent is just, and then here's where it gets really nice. What about its hypotenuse? 1. Does that make sense? For every angle on the unit circle, we end up making a triangle, and that triangle has whatever its opposite is, but that'll just be the y value of the actual point on the circle. Whatever its x value is, or whatever its adjacent value is, but that'll actually just be the x value of that spot on the circle, and then its hypotenuse will always be 1. That is really easy to work with, isn't it? Because 2 of our 3 trig ratios will actually stop being fractions. Does that make sense? Sine of an angle is normally opposite over hypotenuse, but that's just going to be y divided by 1. And then the cosine of an angle is just the adjacent divided by the hypotenuse, which means it's just going to be the x value divided by 1. So for any angle theta, we actually know the cosine and the sine as long as we know its coordinates. Tangent's a bit trickier, but not that tricky. Tangent is just opposite over adjacent. So it would just be take the y value and divide it by the x value. Does that make sense? So we're going to draw that over here, this time to match with you. And we're going to say, for this angle theta, over here, we would have the y value of theta. And down here, we would have the x value of theta, such that we end up with a point, x comma y. All right? Does that make sense?
If you want to draw that symbol, just draw Saturn.
Oh, I like it. Is Saturn my favorite planet? I think Saturn's probably my favorite planet. I mean, Earth, I guess. Earth.
What about Uranus?
But what about Uranus? Yeah. Well, Uranus has rings too, but Earth, definitely. Have you met some of the people here? No, I mean,
What about
that's...
the sun.
It's got to be Venus. Have you heard about Venus? Venus's atmosphere is gaseous hydrochloric and sulfuric acid. So, like, we've landed, like, the Russians landed a lander there in the 70s, and it was able to, like, sit on the surface for, like, 6 or 7 minutes or something before it was just totally eaten apart by acid and stopped functioning. So that sounds pretty inhospitable. Well,
It's got nothing to do. It's just tiny.
The other thing about Venus is that on Venus, a year is shorter than a day. It takes Venus longer to rotate on its axis than it takes for it to revolve around the sun. So imagine if, like, think about that. That's kind of weird, right?
That's a characteristic.
Yeah. Venus also rotates backwards to all the other planets. She's super interesting. Is it like a negative day?
Wake up at night.
Do they say goodbye as they enter a room and hello as they leave?
They don't
Because they're too busy being consumed by acid. Exactly. Okay. How's that feel? Does that roughly make sense? Like, I cannot stress enough about today. Look at me. Everyone look at me. We're going to spend a bunch of days on this. Can I promise you something in advance? In about a page right now, you're all going to have that glazed over eye look where you're like, what is this guy talking about? And you just promise you'll trust me a little bit? Just trust me, okay? Just trust me. Trust me that you're gonna do fine with this. Okay? Ready? Now this means that for any angle on the unit circle, the sine, which is just the opposite over the hypotenuse, but remember we said on the unit circle, what is the opposite? Yeah, the opposite is just the y value. And what is the hypotenuse? 1. And of course, we'll use it in a minute. What will the x value be? The adjacent. So, the sine is the opposite over the hypotenuse, but that is the same as saying it is the y value of the angle divided by 1, which is like saying it's just the y value of the point. Does that make sense? If you draw any point on the unit circle, the y value of that point will be the sine of the angle that you get if you go to that radius. Does that make sense? So if I drew this angle down here, whatever the y value of that is the sine of that angle theta. We're going to erase all that. Ah, damn it. Okay, what about the cosine? Cosine equals what?
Adjacent over.
Adjacent over hypotenuse. Very good.
I remember some stuff.
Oh, you got it all, man. And in this case, the adjacent is what?
The adjacent is x.
Beautiful. And the hypotenuse is?
1.
1, which means the cosine of theta is just the x value, right? And finally, the tangent is a little bit trickier. Tangent is what? Opposite of the angle over the adjacent of the angle, which if it's on the unit circle, and only if it's on the unit circle. Yeah, the truth is with the unit circle, tangent's the least useful, for sure, right? But it's still not that hard, because what's the opposite?
Y.
And what's the adjacent?
X.
X. So that's not so bad, right? So, therefore, on the unit circle, any point xy produces an angle theta with, oh, almost switched them.
Produces an angle. Okay.
Oh, shoot. Does that make sense? As long as we're using the unit circle, and I can't stress enough, this is important. It's got to be on the unit circle. And if you do, then all you have to do is read the coordinates of the point, and you get its cosine, and you get its sine. Does that make sense?
Yeah, I drew Saturn instead of the symbol.
Now, with that in mind, we could go into Desmos. I'll come back to this, I promise. So don't stress if you lost it. You're going to have lots of time. But we could go to Desmos. Sorry, I was helping. Don't worry, you don't have to worry about this till next unit.
Okay.
And actually, those ones are like next year ones. But so if I did, does anyone know the formula of a circle? X squared plus y squared equals the radius squared, which in this case is going to be 1, right? Okay, there we go. And then I could define points such that I could call this like a comma, 1 minus a squared. Does that work? I think that works. Well, nope, that was silly. Square root of 1 minus a squared. This has nothing to do with what you're doing. I'm just trying to make it so that I can put my stupid point. Look here, look here. Look what it does now. Oh, it'll only go in the positives, but that's okay. For what we're doing now, that's totally fine, right? Okay. Oh gosh, how do I get to draw a line? Not that it matters, but I want to draw a line. I can do this. I can do this. Ready? Ready? Instead, I'm going to say b equals the square root of 1 minus a squared. Guys, you do not need to know this, okay? B. I just want a little line here. And then we'll say, we can do this. Y minus, why am I doing this? Y minus b equals, and then this will be x minus a, and this over here has to be b over a. And then we're going to constrain this. All right, ready? Ready? Y has to be greater than 0. Has to be greater than 0. Has to be less than b. Okay, hey, how's that? Okay, there we go. You don't need any of that. But here's what we do want. Ready? Let's label these points. Whatever angle that is, look what it gives me. Do we see that? So right now, if that has a cosine of 0.904. And how do we know that? Well, we know that because that's the x value, and the x value is the adjacent. And how long is the hypotenuse? 1. So can somebody use the cos inverse and see what this angle is? If you do the cos inverse of 0.904, we should get this angle.
Hold on, I got this.
What'd you get?
25.31106.516. And you got to put in all that, and I'm not saying it again.
That's okay. I'm going to, ready? So you got 25.3. And the other way I could get this angle is, what is 0.42753? That is the
Sine?
Yeah, and now I've changed my angle. Can I undo that?
You just did.
Oh, good. We're back. Okay. Yeah, so I could take the sine inverse of that value, and I should get the exact same angle. And notice what I get? The exact same angle. By the way, if I wanted to, I could take the tan inverse, but what would I have to do with these? The tan inverse is the y is the...
I got a different answer.
Yeah, you have to do the y value divided by the x value. Did you do sine inverse of 0.42753? By the way, if it's a little bit different,
I did actually do it.
if you get it a little bit different, that's because this only shows 5 decimals, but it's actually rounding based on like way more. So you may get slightly different answers. Don't stress about that. Do you see how see how that doesn't line up perfectly? That's just because Desmos actually is working with more decimals than we have here. Does that make sense?
Close.
Very close?
It's not there.
Yeah, that's okay. Don't worry about that. That's totally a rounding issue, and rounding issues happen. But do you see how all 3 of these give us the same answer? And so I could set my angle here, and there we go. Pretty funky, eh? Now, right now, this thing won't let me do an angle greater than 180 degrees, but I'm sure with a bit of tweaking, I could figure that out, right? How's that feel?
Pretty good.
All right. So now, I think actually it's as easy as, ready? Times, all we have to do, this is actually easy, a divided by the absolute value of a. And now this should let me go negative. Huh?
Yeah, but you restricted these.
Well, yeah, but that's okay. Oh, interesting. I think I want. Well, yeah, we'll get there. Okay, that's not the full solution I thought it was, but that's half the solution. So Anyway, okay. So there we go. So what do we do with this? Well, what we're going to do next is something that, again, I'm going to make you guys teach and write out tomorrow perfectly. But I've marked some key angles here. And this is the unit circle that we're going to look at all the time. And there's some key angles here that we want to know. And for the moment, we're just going to work in the acute sphere. What do I mean by the acute sphere? Acute angles are between 0 and 90. Does that make sense? So for now, we're going to ignore this whole part of it, though we'll get there. It's easy. For now, I just want to work in the range from 0 to 90, the acute sphere. And this would represent 0 degrees. Of course, it would also represent 360 degrees. This angle up here is how many degrees? 90. Fantastic. Over here, 180. And down here, 270. Okay. If we go halfway to 90, what is this angle here? 45 degrees. And then what if we cut it into thirds? That's what these represent. That's a third, 2/3, and that's all the way to 90. So what do these two represent? 30 degrees and 60 degrees. Okay. For today, these are the angles we're going to care about. 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Does that make sense? And we're going to remind ourselves. We're always, whenever we draw the unit circle, we're going to remind ourselves that for any angle theta on the unit circle, the points are the x value will tell us what about the angle?
Looks like a frowny face.
It does. You're not wrong. The x value will tell us the cosine of that angle, right? And again, the reason it tells us the cosine of the angle is, don't draw this, if that's theta, this x value here represents the adjacent, and because it's the unit circle, how long is the hypotenuse? 1. So x over 1 would be the cosine. Anything over 1 is just itself. So the x value is the cosine of the angle. And the y value represents the sine of the angle. Okay. For any angle on the unit circle, if we can figure out its coordinates, then we can know its cosine and we can know its sine. Now, for most angles in degrees, we don't get nice numbers. Does that make sense? But as it happens, 0 degrees is quite easy. What are the coordinates of the angle 0 degrees? What are the coordinates of this point?
1, 0.
That's right. The x value is 1, and the y value is 0, which means the angle 0 has a cosine of 1, and it has a sine of... Quickly check that. Take the sine of 0 and the cosine of 0.
Sine of 0.
Sine of 0 should be 0, right?
Oh, wait. Cosine of 0 is 1?
Cosine of 0 is 1, which it has to be, right? Because we've already said that if you know its coordinates on here, then you know its sine and its cosine. So that's a nice easy one. What's the other nice easy one in the acute sphere? 90. Because what are the coordinates of 90?
That's not acute, though. That's a weight.
It's true.
I was going to say 45.
0 and... No, 0, 0 is the origin. 0 and 1. And so check that. What should the cosine of 90 be?
0.
0. Check that. Is cosine of 90 0? And what should the sine of 90 be? Good. So thus far, our theorem that on the unit circle, the x value gives us the cosine of the angle and the y value gives us the sine of the angle, it works out, right? Now,
So I got. Wait. So what do we put for the first one? The cosine of what?
try the cosine of 90. It should give you 0.
Oh, cos of 90.
Yep, try cos of 90. It should give you 0.
All right.
Check it out.
Sine.
As long as your calculator is on degrees, right? We got to watch out if it's...
Wait, hold on. Wait, I think.
Anything?
Hold on.
Yeah, you're doing perfectly. Cos of 90 is 0. Sine of 90 is 1. And look up here. That's exactly right, Seth, because if you look, remember, the x value gives us the cosine of the angle, right? And the y value gives us the sine of the angle. So perfect. That's good. What I want to do today is look at these 3 angles. Does that make sense? 90 is easy to figure out because it's just only go straight up, right? 0 is easy to figure out because it's just go to the right. Let's look at 45 degrees, and we're going to use the Pythagorean theorem to do this. So let's say that we have our, and I'm going to draw this to scale. You don't have to, of course, but we're going to draw oh my goodness. I'm so bitter right now.
That's a big triangle.
Yeah, it's bigger than I'd hoped for it to be. I am going to highlight it and move it. But what I wanted was to have 45 degrees, right? And of course, with a right angle triangle, if we're going to call this our theta 45 degrees, what does this have to be? 90, okay. This would be measured up off the positive x-axis.
I'm very sorry for the interruption. Could we have Sophia Cooper in guidance?
Yes, you absolutely could. Okay, yeah, guys, draw that. And while you draw that, guess what I'm going to do really quickly? I'm just going to, look, we can do 2 things at once. Okay.
Hold on, wait. Actually, that reminds me. Can you go back to the first page so I can, real quick?
Yeah, I'd love to. How's that? Is there something specific you want?
Yeah, I just didn't finish writing that there.
Oh, perfect. Yep, you got it. Okay, so, real quick, Critton is here, Evan is here, Sam is here, Lily's here, Sarah's here, Saphira's here, Kayla's here, Aiden is here, Scarlett is here, Kartik is here, Kiki is not, Diana's not, Alexander's here, Angela's here, Annie's here. No, Annie's not here, sorry. Sam is here. Seth is here, Nan's here, Solange is here, post. All right. So, I picked this one as the first one because it's actually kind of easy to work with. And do you know why it's kind of easy to work with? Oh, for goodness sakes. It has a 90-degree angle, but it also has a 45-degree angle. Now, we know that the hypotenuse is how long? By definition, if we want to put it on the unit circle, 1 centimeter. Or not 1 centimeter, just one unit. Right? But now, if that's 45 degrees, what would this have to be? Yeah, and if we're not sure, we know that the angles have to add up to
90.
Yeah, that's right. Because 180, and we've already used up 90, right? And then we used up 45. And if you do that in your calculator, that's going to leave us with 45 degrees. But wait a minute. What kind of triangle is that then? It's a right triangle, but it's also another type of triangle. It's an isosceles triangle. And if it's an isosceles triangle, what has to be true about these 2 sides? They have to be equal to one another. They have to be equal to one another. Therefore, the triangle is isosceles. Oh gosh. All right, who wants to be a real mensch and tell me how I spell isosceles? No, that's an S. I saw. Ready? Therefore, 2 sides equal. ISOCEL isosceles. There's no way that's correct. Like this? Like that? Oh, it's SC. Got it. Well, I feel stupid. Isosceles? Got it. Okay. I trust you. Okay. Now listen. Therefore, let's give these, this is X, right? And we would call this Y. But it means on this particular triangle, X and Y are equal. This will be the only possible right angle triangle where that's true, right? Does that make sense? It is only for a 45-degree angle that this is true, and this is why this is going to be one of only 3 angles that gives us a nice perfect ratio. Does that make sense? It's a special triangle. This is called a special triangle. Ready? Sometimes I feel like a special triangle. My mom says I'm a special triangle. I'll tell you, I've gotten progressively less triangular as my life has gone on, but I think I haven't gotten any less special. Wow, that writing is really special. Okay, so this triangle is special, and could we use the Pythagorean theorem? If we did the Pythagorean theorem, we would get 1 squared equals x squared plus y squared, right? But what do we know? We know that x is just equal to y, which means how could I rewrite that? 1 equals x squared plus x squared. Okay, not too bad. Therefore, 1 equals 2x squared. All right, if I'm trying to solve for x, what should I do here? I could divide the 2 away. Okay, which would mean that now a half equals x squared. And if I want to solve for x, what should I do? Yeah, I could take the square root of it. And I could get, therefore, x equals 1 over square root of 2, which is also y. Does that make sense? Now listen. Listen to me.
Why don't you just square root the whole thing instead of just the 2?
You totally could. In fact, we're going to make this a little bit uglier, but this comes back to a math manners thing. Remember how I talked about there's certain things that are just kind of considered bad math manners? Negative exponents are usually considered bad math manners, so some people like them. Another thing that's kind of considered bad math manners is square rooting a whole fraction when you could just square root half of the fraction, but it gets worse because there's an even quote unquote nicer way to show this. Yeah, and this really is, look here, you don't have to write this, you can if you want. 1 over root 2, as a rule of thumb, it's considered kind of rude to leave a square root in the denominator. We prefer to have a square root in the numerator. So what we do, and this sucks, I hate this, but this is what we do. This is considered good math manners. If I multiplied this bottom by square root of 2 again, root 2 times root 2 would be root 4, and the square root of 4 is just 2. So that takes away the square root sign, which is nice. But to make it a fraction, I also have to multiply the top by root 2. So 1 over root 2 is the same thing as saying root 2 over 2. And that's the preferred fraction. I'm sorry. This is the preferred way of showing 1 over root 2. If you wrote 1 over root 2, would I care? No, I'd say, that's cool, I get it. And I'd probably put a little note that say, Mr. Calford would prefer you put root 2 over 2, and I do what Mr. Calford tells me. Okay, so this is true, but instead what we write is that x and y are both root 2 over 2. Yeah.
X.
Now, to be clear, what would be a better way of writing that? Exactly what our friend Seth said. Is that clearly better?
Yeah.
I think so. But how don't they write it? Like that. Math teachers, boy, they love their making things difficult, right? This is the making it difficult way.
They like watching kids cry.
No. But do you think Alfred likes watching kids cry? I do not like watching.
Never mind that. Mr. Calford's gonna get some popcorn.
Can I tell you, every once in a while, physics was the worst for it. I felt like when I teach physics, every once in a while you hand a test out, and you'll look out and you'll see not one, not two, but like 3 people crying, and you're just like, what am I that I'm like making multiple people, like that my job involves making multiple people cry at a moment. It really like messes with your head.
You're gonna be really excited for physics next semester.
You know what? I really miss teaching physics. I haven't taught it in years, and Alastrek has it this year.
Yeah.
But I have chem, so that's exciting. Is that serious or sarcastic?
No, I'm not.
Oh, good, because it sounded sarcastic, and I was like, I'll try to make it fun. Honestly, can I tell you, chem and physics are really fun. I think. I mean, your mileage may vary. I find them really fun. Okay.
I didn't really like it. To be honest.
So, which one?
Chemistry.
Well, but you haven't taken it like in grade 11 yet, though, right? Have you?
No.
Like you weren't in Alastrek's class last year, were you?
No.
No, because like his class was a blast. People had a lot of fun. Okay, so do we see that? That is really useful because it means for the angle 45, what x value do we get? Root 2 over 2. What y value do you get? Okay, let's quickly do this. On your calculator, well, let's first write it here. What are the coordinates of 45 degrees then? The x value is root 2 over 2. And the y value is root 2 over 2. Now, let's just check this then. On your calculator, quickly do root 2 divided by 2.
Better every time Mr. Orlando says root 2 over 2, take a drink.
No, I won't be drinking. So square root of 2 divided by 2 gives us 0.7071, right? Okay. But now, did you get the same? Annoyingly, on those yellow they have a square root button. They don't have a cube root button. Okay, now try this. What does this x value tell us about 45? Remember, on the unit circle, what is true? For every angle theta, the point on the unit circle that represents that angle, its x value is the cosine of that angle. So can we take the cosine of 45? What should it give us? It should give us root 2 over 2, which is 0.707106781186548. What about the sine of 45 degrees? The sine of 45 degrees is root 2 over 2. How's that? Is that not too bad? Is that just bad enough?
Yeah.
Just bad enough? Okay.
Getting worse.
I'm offended. No, I'm not offended. I appreciate that. No, this stuff's a little weird, right? But do you see how the unit circle isn't meant to make things tricky? It's actually meant to make doing trigonometry easier. Does that make sense? Because if you can just find the coordinates of the point, then you've got the sine and the cosine, right? If you can just find the coordinates of the point, you've got the sine and the cosine. Which, by the way, what is this basically? Well, it's basically a protractor. Does that make sense? Only instead of being for degrees, it's a protractor for sine and cosine. Does that make sense? If you wanted to, you could take this, you could put an image on it, and you could just line this up, and it would tell you what the sine and the cosine are. By the way, what is my sine right now? Well, that's interesting. My sine is negative. We'll get to that in a minute. Don't worry about it. In fact, we won't get to that in a minute. We'll get to that tomorrow. Okay. There's another special triangle. Now, if you didn't leave room for the second special triangle, that's okay, actually, because we're going to do a day that is just practicing our special triangles, but I'm going to do the second one here. Look at me.
actually have lots of room. So.
Excellent. If you don't have room, don't stress. You're going to do a whole note just on reminding yourself of these proofs. The nice thing with the unit circle is you won't have to recreate this. If we learn the unit circle, then you're not having to draw your special triangles and remember them. But our second special triangle, the only other triangle that's going to give us both a 90 degree and another easy degree, is another special kind of triangle where all of the angles are 60. What kind of triangle does that make? It makes an equilateral triangle where every angle is 60 degrees. And if all the angles are 60 degrees, then what else is true? All the sides are equal to one another. Okay, don't fight. Don't fight. Don't fight. It's okay. So in our second special triangle, we're going to do this, and we're going to get 60 degrees, right? And 60 degrees. But then here's what we're going to do. Because what this doesn't actually give us is 90, right? Now the good news is this would be 1 unit, right? And this would be 1 unit, right? But here's what we're going to do. We're going to say that isn't very exciting because the whole point of the unit circle is I need that 90 degree angle, right? Well, watch this. Is everyone excited? Are you excited? Watch this. Ready? I'm going to give you a 90 degree angle to work with. I'm splitting it down the middle. Seth has called it correctly. There we go. Yeah. Now we have a 90 degree angle here. And what angle do we have up here? We have 30 degrees. Oh, no. What? Okay.
Don't ask, it's so stupid.
It's what?
I think it's the target audience. It's not like any the condensation age turns it into a mode.
Oh wait, I see what you did. So you took 180.
I don't know.
You subtracted it by 60 twice. And since you split it down the middle,
Yep.
it's divided by 2.
Beautiful. Very good. Okay. Does this make sense? Do we understand why we get 30 degrees up here? What's this angle over here? 30, making this total 60. This one's 60, that one's 60. But now, here's the kind of cool thing. This is why we also get nice angles for 30 and 60, is we can use the Pythagorean theorem here. All right? Because the top of this thing is, the slant here is 1, which means, will this fit on the unit circle? Yep. How long is this down here? Yeah, the whole thing here would be 1. 0.5 is the right answer. I'm going to work with a fraction. I'm going to say a half, but 0.5 is correct. Right? And then what about this here? Well, I don't know. Can we figure it out? Let's figure it out. Okay. So already we've got an x value for 60, right? Does that make sense? But we don't have the y value yet. But having said that, we have the x value for 60. On the unit circle, what is the x value?
1.
No, what is the x value?
Oh, cos.
It's the cosine. We should already know the cosine of 60 degrees. Can you try that? Type in the cosine of 60 degrees. What should it equal?
0.5.
Look at that. Isn't that kind of cool? The unit circle. She works. So now we need to figure out the sine of 60 degrees. In other words, we need to figure out the y value. Well, how do we do that? Well, we know that 1 squared in this case will equal what? Why would I put an x there? I'm so stupid. What should I have put there? A y. I'm sorry. I do not know why I put an x. In fact, I should have put x equals a half. Right?
Yeah, I was gonna question.
Yeah, you should always question me. Team, you know what you should spend all of your day doing? Questioning me. That's what you should do. So 1 squared equals, in this case,
Where were you?
A half
November 17th at 11:57
squared
p.m.
plus y squared, right? Okay, this isn't too bad.
Yeah, I kind of put it backwards. Oh well.
That's totally okay. Can we square 1? What do we get? 1. Can we square a half? What do we get? Careful. A quarter is correct, right? Do we want to show the intermediate step of 1 squared over 2 squared? Maybe not a bad idea, right?
1 squared is 1, 2 squared is 4.
And so that gives us 1 over 4 plus y squared. Now, if I want to solve for y, I should obviously get rid of,
The squared?
eventually, what should I get rid of first?
The
quarter.
quarter.
And I got to do that to both sides, right? What is 1 minus a quarter? I could find a common denominator, but I think you can do that. You've done this before. You have $1, I take away a quarter. What do you have left?
75 cents.
75 cents, also known as 3/4. Does that make sense? And what does that equal? Y squared. But if I want to know what y is, what do I just have to do? I just take the square root. So I would take the square root of this side, and I would take the square root of that side. And is everyone comfortable if I give this the old mathematical term now? The old flipperoozy? Okay. So y is just the square root of 3 over 4. But as we discussed, this would make a math teacher grumpy, especially because what can you actually take the square root of here? Can you take the square root of 3?
No, but
No.
you can take the square root of 4.
You bet I can. What do I get?
2.
Very good. So what we end up with is root 3 over 2.
Okay, I think I get it.
So take a look here. For the angle 60 degrees, the opposite ends up being equal to root 3 over 2. And the adjacent ends up equaling, well, we already knew this, a half. Let's quickly do this and put it on the unit circle. If we go up to 60 degrees, we can say that the x value, the value on the bottom was a half, right? And the y value was root 3 over 2, right? Yes, 2 seconds, but yes. You have precisely predicted where we're going next. All right. And so now, really quickly, let's just make sure this is true. What is root 3 over 2 expressed like to the nearest decimal? 0.860254037844439 ... keeps going forever. Do it on your calculator. Make sure that's what you get.
Oh wait, I forgot to do that. Yeah,
Great.
0.86602540388.
Great. What should the sine of 60 degrees equal? Based on what we know of the unit circle. 0.866025430784439. And lo and behold, what do we get?
0.8660254.
Awesome. What should the cosine of 60 be?
The cos of 60 should be 0.5.
Very good. Very good. Does that make sense? The unit circle hasn't failed us yet. Now, I could draw a whole nother special triangle, but what angle do we actually already have all the information we need for? 30. Now, do you see what I mean where I say, like, I'd have to change which side I cut in half, right? Do you see that if I had done my ... here, would I get the same numbers?
Yeah, maybe.
So for 30 degrees, and I actually am going to sketch this just quickly, all right? So if I draw another equilateral triangle of 60, 60, but now I cut this in half such that this is 30, right? We're going to get all the same numbers. I'm actually not going to sketch it. I don't care. Just for 30, the opposite is what? The opposite is a half. And for 30, the adjacent is?
Square root of 3 over 2.
Root 3 over 2. So for 30 degrees, we're going to get the exact same numbers. They're just going to be transposed. Does that make sense? So instead of it being, instead of 1/2 being the x value, now 1/2 is the y value. So that'll be 1/2 over here. And what's the x value now? 0.86607 blah, 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 which we could just write as √3/2. These are the only angles expressed in degrees that have clean trigonometric values. Does that make sense? The only acute angles, I should say. That is √3/2. And I'm going to make you memorize this, but it actually memorizes really easily. Look at me. Ready? Let's look at the x values. And remember, the x value is the cos of this angle, right? So first of all, what are the angles that have special trig values? 0, 30, 45, 60, and 90. Very logical.
What
right?
happened to 15? What happened to 75?
They don't have nice trig values.
Oh, okay.
You can't draw a nice right angle triangle for them that gives you exact values. Does that make sense?
Oh, okay.
Good question, by the way. So now, with that in mind, with those all being the only ones that have nice values, how do the values change? Well, the x value, which again is for every single angle on the unit circle, the x value is its cosine. It starts at 1. Now listen, there's nothing special about this. It just happens to be true, but it makes memorizing this very easy. Look at me. 1, and then √3/2, then √2/2, then 1/2, and then 0. Does that make sense? Again, it's just a trick. It just happens to be the case, but it makes memorizing it so easy. 1, √3/2, √2/2, 1/2, 0/2. And then what happens with the y values?
0/1.
They go in the exact opposite. 0, 1/2, √2/2, √3/2, and then √4/2, what's √4/2? Well, √4 is 2, 2/2 is 1. So you could almost think of it as √0/2, √1/2, √2/2, √3/2, √4/2.
Good morning,
That's a
Eagles.
stupid
On
way to
today's
think of it,
cafeteria
but
menu, we have
do you
chicken
see how that
sandwiches
memorizes
for
easily?
$2,
Okay.
also both salads for $4, and are featured on
Tomorrow,
grilled cheese,
we're going to
french
work
fries
with
for
this and
$5,
say,
and
what
for
happens when we
$2
go the other 270 degrees? But you could probably figure that out all on yourself just looking at it. Because really, what's going to be the only difference between this point and that point?
The x is going to be negative.
The x is going to be negative. What's going to be the difference between this point and that point?
The y is
The y and the x's are negative, right?
Y and X.
And then what's the difference between this point and that point?
Just y.
Just the y is negative. Does that make sense? Which you can try this really quickly. If you take down here, all of the y's are negative, all the x's are positive, right? Which means down here, between 270 and 360, all of the cosines are...
Oh, wait, that's why you kept going down there on decimals.
Yeah.
When you set everything to negative,
That's
it
right.
wasn't just one specific thing going to negative.
Yeah,
Those
so
things were-
any angle in here, the cosines are all going to be positive, but the sines are all going to be negative. You can try that. Take the sine of 300 degrees. I don't know what it is, but I know it's going to be negative. Take the cosine of 358 degrees. I have no idea what it is, but I know it's going to be positive. Does that make sense? So the unit circle is a powerful tool that we use in math all the time. Can I ask, you don't have to recreate these, but do they make sense? I don't expect you to recreate them, but you probably could, right? To figure out the trig values of 45 degrees, we just made what kind of triangle? Well, right angle, where two of the angles are 45. And then to get 60 and 30, we made an equilateral triangle and we just cut it in half. Does that make sense? Does that feel okay? Now again, the truth is, what I like about the unit circle is, if you can remember this, you don't have to recreate the special triangles, right? You can just, this little trick. And the other nice thing about this is, then when we get an angle here, we may not know the exact value, but you could be like, oh, I don't know what the cosine of 15 degrees is, but I know it's between 1 and root 3 over 2. You know what I mean? It at least gives you some information. Does that make sense? So again, you can think of the unit circle as like a big protractor, but instead of giving you the angle in degrees, it gives you the sine and the cosine of the angle. Does that make sense? It's like a big old sine cosine protractor. How's that? Not too bad? And again, if we wanted to find tan, the tangent of the angle would be what? Well, tangent is opposite, which is sine, over adjacent, which in this case is the x. So if you want to find tan, it is trivial. It's not a super difficult thing. What would the tangent of this be?
That would be root 2 over 2.
Yeah, the tan of 45 degrees is actually the nice easy one, because it'd be root 2 over 2 divided by root 2 over 2. But anything divided by itself is just 1. Take the tangent to 45. What should you get? 1. Try that. See if that's true. You got 1? There you go. So we'll work with this more tomorrow, but on a scale of 1 to glassy-eyed, how are we feeling?
1 to what?
To glassy-eyed. Just 1. I'll take just 1. Yeah, and again, what I want to encourage you is, if you understand this, awesome. But even more importantly, we're going to use this as a tool. You know what I mean? Could you build a calculator? Probably not, but I bet you can use one. Would I love it if you can build the unit circle because you totally understand it? Yes, that'd be awesome. But even if you can't, we're going to, what the heck was that? No, I liked that. I like that. Guys, have a wonderful day. Be kind to one another. Don't do anything that Kryla over there wouldn't do. Kryla, how was your weekend? You said you were tired last night?
You